Electrical energy is one of the most powerful forces on the planet. While we appreciate the benefits it offers society, we must also respect its ability to cause damage, personal injury, and even death. Each of us must take personal responsibility for electrical safety. The focus of this program is to increase your awareness of the safety issues faced by individuals who work on or near electrical equipment, and offer suggestions on how you can protect yourself and others from potential injury and death. Statistics tell us that more than 4,000 non-disabling and 3,600 disabling electrical work-related injuries occur each year in the United States. Every 36 hours, someone is killed by electrocution in the home, while in the workplace, on average, someone is electrocuted every single day. How can we protect ourselves against this energy? Hazard awareness, knowledge of safety procedures, a system designed with safety in mind, proper planning and preparation are all essential elements of a safe workplace. Each of us must take responsibility for their implementation and practice. There's no doubt about it, electricity can be dangerous, and safe work practices must become second nature. This program will help you better understand safety basics. There are three main hazards associated with electrical energy: electrical shock, arc flashes, and arc blasts. All electrical shocks are significant, and there are only two degrees of shock: discomfort and death. The degree of significance depends on the magnitude of the current, the path the current takes through the body, and the duration of exposure. Electrical shock at any voltage is a serious issue. Any contact with voltages above 50 volts could result in a tickle sensation, injury, or even death. The only difference could be a few hundredths of an amp. When an individual is shocked, electrical current typically travels through the body along one of two conductive paths. The current may flow along blood vessels, and this can cause cell tissue damage, swelling, and circulatory problems. While these injuries may not look serious, the body can actually be burned from the inside out. Complications from this type of injury often require amputation of the afflicted arm or leg. Electrical current can also travel through the nervous system. Here, the result is a total loss of muscle control. This table shows how the body reacts to various levels of electrical current. At current level as low as 15 milliamps, an individual's arm can lock up, making it impossible to let go of the conductor. This is sometimes referred to as the let-go threshold current. They may also be unable to speak or call out for help. The longer this continues, the greater the potential for serious injury. Current passing through the heart is another critical concern. Current here disrupts the heart's normal electrical conduction, changing the heart's rhythm, and can lead to cardiac arrest. Fibrillation of the heart can occur with less than 75 milliamps for a half a second. This is about the same current required to light a 7.5 watt, 120 volt lamp. It's important to note that electrical shock and even electrocution occur at current levels below those required to operate for a circuit breaker or current limiting fuse. These devices simply are not designed to operate at such low currents. Only ground fault circuit interrupters can provide sufficient protection from electrical shock. The second hazard associated with electrical energy is the arc flash, which can cause severe equipment damage as well as burn injuries to the body. This video clip will give you a feel for what an arc flash can do. Most electricians have seen equipment damaged by an arc flash. Others may know of someone who was directly involved in an arc flash accident. This type of accident can occur simply by dropping a screwdriver in a panel. It happens fast and can take a serious toll. Notice the explosive movement of fire and molten material. It wasn't until the mid-90s that the U.S. Occupational Health and Safety Administration and the National Fire Protection Association began referring to arc flash as an electrical hazard. Research continues to help us understand arc flash events. For example, we've learned that temperatures near the arc can escalate rapidly to 35,000 degrees Fahrenheit. Compare this to the melting temperature of copper, which is 1,981 degrees Fahrenheit. The real concern is what arc flash energy can do to the human body. Skin tissue is very sensitive to heat. Consider how easy it is to receive a sunburn. Tests indicate that after only 6 hours at 110 degrees Fahrenheit, cell structure will start to break down. At 158 degrees Fahrenheit, cell destruction occurs in about 1 second. The skin's exposure to temperatures of 200 degrees Fahrenheit for only 1/10 of a second will cause incurable third-degree burns. Imagine the effects of a 35,000 degree arc flash. An arc flash can also generate enough light to cause serious injury to the eyes. It's not uncommon for an electrician to report having cataracts up to 3 years after an electrical arc flash accident. A third, often unrecognized electrical hazard is the arc blast. An arc blast is the force caused by the rapid expansion of air and the transition of solid conducting materials into vapor. This expansion of solid material to liquid and then into a conducting gas is significant and potentially very dangerous. When an arc flash occurs, copper conductors, contactors, and terminals can vaporize. This vapor can occupy more than 67,000 times its original volume. The rapid expansion of air surrounding an arc, the blast, creates incredibly destructive pressures and noise. In essence, an arc blast is a massive explosion that can cause circuit components like contactors and relays to explode violently. Adding to the problem are the magnetic forces that propel plastic and metal parts, contributing to the explosive forces of the blast. Imagine the possible injuries caused when flying shrapnel strikes individuals working near the equipment. The concussion alone can easily throw a person off a ladder or across the room. This following test was conducted at the Paul P. Gabani Center for High Power Technology in St. Louis. The mannequin shown here could easily be you or a close friend. A screwdriver on the line side of the overcurrent device was used to initiate the fault. The arc flash in the square overhead duct was unexpected. A piece of the exploding duct hits the mannequin in the forehead. If this were a person, he or she would likely become a fatality statistic. This video also illustrates a common situation, an unexpected event. The lesson here is that we should always be prepared for the unexpected. Let's look at it again in slow motion. This time, pay close attention to the fireball surrounding the mannequin. A concussion of this nature could easily knock the air from a person's lungs. Certainly, it would surprise them. The typical immediate reaction would be to gasp for air, in which case the victim would inhale enough of the hot copper vapor and molten material to cause significant lung damage. The extreme noise would damage the individual's hearing. OSHA has identified 85 decibels as the level above which hearing protection is necessary. The noise level from the arc blast in this test reached 141.5 dB. The point is, in an electrical accident, the victim's skin, ears, eyes, nervous, muscular, and skeletal systems, as well as internal organs, including the heart and lungs, can all be affected. Each of us is personally responsible for electrical safety. Management has ultimate responsibility for the system's control and safety. Managers and supervisors must be aware and knowledgeable of all work performed on the system. This does not mean that they must comprehend all the technical details involved in the job, but a general understanding is required. In effect, management is responsible for the actions of all parties performing work on the electrical system. Maintenance personnel must take all necessary steps to assure that the system on which they plan to work is de-energized and properly isolated. They are also responsible for individual personal protective devices, such as locks and tags. Outside contractors must also possess a thorough understanding of the system, including how it can be isolated from energy sources. They must be aware of and able to comply with the company's safety procedures. And whenever possible, contractors should add their own lockout-tagout devices to appropriate isolation points. So far, we've identified the 3 main hazards associated with electrical energy. We've also determined that each of us must take ownership of safety in the workplace. One question remains. What can we do to prevent future accidents and injuries? The answer is that while we cannot totally eliminate electrical hazards, we can be very effective at reducing exposure if we balance our focus among three key areas: training, planning, and written procedures, providing an electrically safe work environment, and designing the electrical system for safety. Let's start with training, planning, and written procedures. Electrical safety starts with education and training, planning for each job, and preparing written procedures. To reduce electrical hazards, we need to address each hazard as the work is being assigned and planned. Here are some principles that will help ensure a safe workplace. Plan every job. Most accidents occur when something unexpected happens. Take the time to prepare a plan that considers all possible eventualities. Before you start the job, think about each step and try to visualize the potential for a hazard. Conduct a flash protection boundary analysis. The NFPA 70E Section 2-3.3.3 has adopted a new requirement to define the safe work distance from potential arc hazards. Anticipate unexpected results. When thinking about a job, break each task into small steps. Understand that plans can change, so be ready to modify the plan if necessary. Make sure that everyone involved in the job is working according to the same plan. Whenever work is required near an electrical hazard, a written plan is needed to outline the scope of the job. Use procedures as tools. Procedures are the best way to help you prepare, execute, and complete the job. Like any tools, make sure your procedures are maintained. Identify the hazard. After your work plan is complete, review each step. Consider that the equipment might be perfectly safe under normal conditions and very unsafe when systems are not working properly. Also, consider potential hazards that may be unrelated to electrical energy. Assess people's abilities. Any person assigned to tasks associated with electrical energy must be qualified and trained for the job at hand. He or she must be able to identify electrical hazards, avoid exposure to those hazards, and understand the potential results of all action taken. Don't forget to include yourself in this analysis. And don't forget to establish and maintain training records. There are also a number of principles that apply to the second focus area, providing an electrically safe work environment. Use the right tool for the job. Use the appropriate tools for the job at hand. Keep them accessible and in good working condition. Using a screwdriver for a job that requires fuse pullers is an invitation to an accident. Isolate the equipment. The best way to avoid an accident is to reduce exposure to hazards. Keep doors closed. Keep barricades in place. Install temporary voltage-rated blankets covering exposed live parts. Protect the person. Use the proper personal protective equipment for a job. This may include safety glasses or goggles, head protection, voltage-rated gloves, safety belt and harness, or flame-resistant clothing. Minimize the hazard. If it is impossible to establish an electrically safe work environment, be sure to shut down every possible energy source. Understand that sometimes a de-energized circuit can become re-energized, and do something to lessen the risk. Audit these principles. A principle is something you believe in enough to be willing to do. Are you willing to take the steps necessary to avoid injury? Review these principles often. Add to them when necessary. Our third focus area, designing an electrical system for safety, comes with its own set of guidelines. Isolate the circuit. Electrical systems must be designed to support preventative maintenance with easy access to the equipment. Designers need to make it easy to isolate equipment for repair with a disconnecting means that provides for proper implementation of lockout-tagout procedures. A sound design should also provide optional disconnecting means at all motor loads. This is in addition to the disconnect required at the controller that can be locked in the open position. Disconnects at the motor will provide improved isolation and safety for maintenance and for use in case of an emergency. An orderly system shutdown should also be required to minimize the hazards to personnel and equipment resulting from an electrical event. To address this situation, the National Electrical Code provides for a system of coordinated overcurrent protection devices. Cover exposed components. Equipment must be finger safe to avoid potential contact with energized conductors. It is not always possible to de-energize the equipment before working on it. If energized metal components could be exposed during routine maintenance, covers, shields, and insulating barriers must be used in accordance with safety standards. Limit the energy. Circuits should also be designed to limit the available arc flash energy. The use of smaller or higher impedance transformers and current-limiting overcurrent protection devices will help to reduce the flash energy. This will provide improved protection for both equipment and employees. Many companies are going one step further by specifying Type 2 no-damage coordinated protection for motor starters. This not only reduces the damaging energy seen by the starter, but also helps to reduce the flash energy seen by employees. Please review the following two clips and observe the difference between an arcing fault using a non-current limiting device and the same circuit using a current limiting device. In this test, the circuit is protected by a non-current limiting power circuit breaker with the short time delay set at 12 cycles. This unfortunate worker may never go home again. To demonstrate the advantage of current limitation, the next test uses a 601 amp Class L current limiting fuse to protect the same circuit. Notice the dramatic reduction of arc energy and gases. This worker may get home yet tonight. Using current limiting circuit protection will significantly reduce the flash hazards that are associated with high energy arc flashes. An effective safety program pays dividends. Dividends in both economic and human terms. Anytime an accident occurs, the employer experiences some interruption of production. Equipment can be damaged and insurance costs can skyrocket. The employer may face litigation and legal expenses and receive a significant OSHA fine. He or she can even face prosecution in criminal court. Accidents can be expensive enough to put the company out of business, leaving the owner and employees looking for new jobs. The survivor of an accident can be affected on a permanent basis. Many victims lose arms or legs. Some face blindness and disfiguration, resulting in severe depression, withdrawal from society, or divorce. Medical expenses can soar as reconstructive surgeries and physical therapy take their emotional and financial tolls. Addressing the hazards associated with electrical energy is critical to every individual and company. Implementing an effective electrical safety program is simply the right thing to do. It begins with a safe electrical system design. Take the time to learn safe work practices and procedures. If you need help, please check out the following resources.